Comparative or Homology Modelling Part 2. So just to remind you that there are 8 steps in comparative or homology modelling, and in the first part we talked about identifying the templates or parents and then aligning the target sequence with the parent or parents. So in this second part we're going to go through the steps of then actually building a model. So step 3 in the overall process is to identify the SCRs and SVRs. These are structurally conserved and structurally variable regions. Now, a reliable definition of these is only possible if we have multiple parents. So what we would do would be to fit those parents together in 3 dimensions and look to see which bits have conserved structure and which bits have variable structure. Where there's only one parent, we assume that everything is structurally conserved, except where there's an insertion or deletion, and that will almost exclusively be in loop regions. Where an indel does occur in a loop, then we define the whole of that loop as being a structurally variable region. So here's an example where I've taken 2 protein structures and fitted them together, and you can see that these 3 loops up at the top, which I've circled in red, are quite variable in their structure. The one over on the right, I believe one of those loops is one residue shorter than the other, but the rest of the structure is really quite conserved. Now remember that the structurally conserved regions and structurally variable regions are structurally conserved and variable. So this is not necessarily related in any way to sequence identity or sequence similarity. If you have a homologue of known structure with 75% sequence identity, this does not mean that 75% is structurally conserved and 25% is structurally variable. Yes, the amino acids are different, but that doesn't mean that the conformation of the backbone will be different. So that doesn't mean that the structural differences will be distributed throughout the structure, and it doesn't mean that those structural differences will necessarily occur wherever there's an amino acid difference. Indeed, you could have low sequence identity and essentially identical structure throughout, as we saw with hemoglobin and myoglobin. But if there are structural differences, they will be in particular regions. And you need to look at the sequence alignment in the context of known structures to identify where there are insertions and deletions in order to identify structurally variable regions if you only have one parent, and if you have multiple parents, you can make use of those to see where the structurally conserved and variable regions are. So here I've taken the same picture that we saw previously, and this time I've cut the loops off, which was structurally variable, and left just this structurally conserved framework that was supporting those few loops. Given that we have all that structural conservation, then essentially what we do is just copy those backbones to make our new model. If we have a single parent, then we just copy the structurally conserved regions directly. If we have multiple parents, it's a bit more complicated. What we need to do then is fit them in 3 dimensions so that all parents are in the same orientation and location, and then choose each structurally conserved region from one of those parents. Now, to do that, we could look at factors such as the local sequence identity or similarity to the target sequence. We could look at the local RMS deviation, in other words, structural similarity to an average structure of all the templates. Now you might say, why not just use an average structure? But the problem with that is that the geometry will be bad. We'll get bad bond lengths, bad bond angles, and so on if we just average things. So you could average and then just choose the one that's closest to that average, in other words, the one that's most representative. We could look at things like low temperature factors in the crystal structure of the parents. So the temperature factor is a way of measuring how flexible, how dynamic a particular atom is, but it also can be a way of showing regions in a structure which perhaps aren't as accurate. We could also look at the length and or the sequence of the adjacent structurally variable regions, making the assumption that the conserved regions are in some small way influenced by the adjoining structurally variable regions. And there are lots of other things that one could think of as ways of choosing which parent to use. Having multiple parents helps you with identifying structurally conserved and structurally variable regions with more confidence. But at high sequence identity, greater than 70% or so, having multiple parents doesn't generally result in a better model. However, at lower sequence identity it may help, but that ends up depending on the individual protein. Step 5 in the process then is to build the structurally variable regions, and these are almost always loops. So here I've shown a picture of a typical loop of about 10 amino acids. Structurally variable regions, as I said, are almost always loops, and they are built with lower accuracy than the rest of the structure. Now, I said with having only one parent, you would only define the loops that have insertions and deletions as being structurally variable. But that's not necessarily true, because even when length is conserved, loops can adopt quite different conformations because of the particular side chains they have. There are 3 major approaches to building these structurally variable regions. You can do it by hand, taking the parent structure and using molecular graphics software to modify that structure, but really that's very rarely done these days. It was the sort of thing people did 30 to 40 years ago. Secondly, you can use knowledge-based methods. In other words, you use a database of loop structures collected from other proteins, and these most likely will not be homologs. However, in order to search that database, you use factors such as the geometry of how the loop attaches onto the structurally conserved regions. You make sure that it's the right length. You might look at the secondary structure of the adjoining regions and only choose a loop that connects the same types of secondary structure, for example 2 beta strands. You might also look at sequence similarity, and you might also look at making sure that there are no clashes with the rest of the structure. The third approach is known as an ab initio approach, which attempts to search all possible conformations for the loop using some sort of conformational searching process or molecular dynamics, which is a computational way of simulating the movement and dynamics of a protein. Now, both of these overall approaches, either the knowledge-based or the ab initio approaches, will actually generate lots of potential conformations. So you have to choose between these. You want to select one best, most likely conformation for the loop. Now, I've already mentioned energy as one of the things you might do in order to screen your loops, but in addition, you might then want to rank them based on the lower energies that you have accepted in that first screening step. You might want to look at compactness of the loop, in other words, avoiding it sticking out into the solution. Right, it's more likely that it would pack down onto the rest of the structure. And you also might want to look at things like solvent accessibility, in other words, how easy it is for a water molecule to access different bits of the loop, and in particular, making sure that you're burying hydrophobic amino acids and exposing hydrophilic ones. Step 6 in the process then is to build the side chains. So at this stage we have got the backbone of the protein completely constructed, and we have probably still got the side chains in place, but some of them will be incorrect because obviously there are mutations between the parent structures and the target structure that we're trying to model. Now, the simplest way of doing side chain replacement is known as the maximum overlap protocol, or MOP. And essentially what we do here is inherit the torsion angles from the parent side chain, and if we're making a side chain shorter, we just cut it off at the appropriate position. If we are building a longer side chain, then we just build the additional atoms using a standard conformation. So in this example, I'm taking a parent structure which had a serine, so this is the backbone N, C alpha, C O, and this is the side chain, and I'm replacing it with a tyrosine. So we inherit this torsion angle, this twist angle between the C alpha and the C, which means that the C gamma position here ends up in the same location as the oxygen was here. And then the orientation of the rest of the side chain is built in a standard way. Now, that approach is all very well, but it actually throws away useful information. And this useful information is what's known as a Rotima library. So there's always a preference for staggered conformations. In this view on the right, this is what's known as a Fisher projection. And the small circle is an atom that is close to you, and the big circle is an atom that's farther away from you, and the two are bonded to one another. Now we've got, for the front atom, an oxygen and two hydrogens attached to it, and for the rear atom we've got a carbonyl group and two hydrogens attached to it. So what we find is that these staggered conformations, where there's a step of about 60 degrees from one atom at the front to an atom at the back, are preferred to the eclipsed conformations, which would be achieved by rotating by this around this bond from the back large atom to the front small atom. If we rotated by 60 degrees such that this atom was on top of this one, then that would be an eclipsed conformation. But not only that, not only do we have a preference for staggered conformations, but also we have a preference for particular staggered conformations. So what I've done here on the left is select about 50 tyrosines completely at random from the protein data bank and fitted them on their backbones. And what you can see from that is that we have one quite tight cluster here, one slightly looser cluster here, and then one example in that third conformation here. So these are reflective of the three staggered positions, and you can see that there's a preference for this one, closely followed by this one, and then this one with hardly any. Now if we look at the same thing with phenylalanine, here the preference is very clearly for this left-hand conformation, followed by the one over here, and then there are no examples in that third conformation. So we can use this information, which is residue dependent, to suggest what is the most likely conformation for each amino acid, but we can also make use of the alternative positions. So there is a program called Squirrel which puts all the replacement side chains in their most preferred Rotima position and then looks to see if there are any clashes. If there are any clashes, then residues are moved to their second most preferred position and we re-evaluate. And essentially the software keeps iterating until it's found a position where all the side chains are happy. And in general, this sort of approach will outperform simple maximum overlap protocol approaches. The seventh step in the process is to refine the model. And there are two ways of doing this. I'm not going to go into any details about these, but they're known as energy minimization and molecular dynamics. And both of these approaches essentially treat a protein as a set of Newtonian springs obeying Newtonian physics. And that allows us then to have optimum values for bond lengths, angles, torsion angles, and so on. And you can treat any movement away from that optimum as if the atoms were forming a spring. We also have optima for van der Waals packing, that's the interactions between atoms when they're just touching each other, and for electrostatics, so charge interactions. In molecular dynamics, what we do is assign an initial velocity to each atom based on a Boltzmann distribution. And then from the positions of the atoms, we can calculate the forces. Given that force equals mass times acceleration, we can then calculate accelerations. We can take a time step based on the velocity and move each atom to a new position. We update the velocity based on the acceleration, and we keep doing this over and over again, and that has the effect of iteratively integrating Newton's laws of motion. In energy minimization, we aim to move the atoms to an energy minimum. Now, the reason that we need to do all these things is because when we've spliced together bits of structure, structurally variable regions from one place, structurally conserved regions from another, then the joins between these may have non-optimum bond lengths and bond angles, there might be clashes, and similarly when we do the sidechain replacements, although even if we're using something like Squirrel to optimize those, there may still be some minor clashes. So energy minimization would allow us simply to move things to a more favoured position. However, the problem with energy minimization is that it can only make very small movements to atoms, and it can get stuck in what's known as a local minimum. So you can imagine a surface which is very rough, and at some point on that surface there is a real big dip in the surface, which would be the minimum energy position. And if you're trying to roll a ball over that surface, it's quite likely to get stuck in one of those little local pockets rather than falling into the biggest pocket. And if you think of a protein structure as being a hugely multi-dimensional surface, there are going to be lots of these little pockets on that surface. Molecular dynamics, on the other hand, because you're putting energy in the form of heat, it's actually able to escape from these local energy minima, and you can then be more likely to find the global energy minimum. In the final step 8, we evaluate the quality of the model. Now, normally you do not know what the correct structure should be. And so we have to use methods that basically look at a protein structure, or a model of a protein structure, and try to evaluate how likely it is that this is correct, just based on its intrinsic properties. And a common way of doing that is to use what's known as a pseudo-energy or statistical potential. And methods such as analyia and Q-mean do that, and they essentially just look at the environment of each amino acid or each atom, depending on the particular method, to look how happy it is. So, for example, two hydrophobic residues like two valines are likely to be close to each other and have a preference to be interacting. Whereas if we took two positively charged residues like two arginines, they would prefer not to be close to each other. So we can look at the environment of each residue, look at what other residues are surrounding it, and see whether or not it's likely to be happy. So this will be covered in a bit more detail in the practical itself. There are instructions about using these types of software, and you're expected to learn some information from the practical as well as from the lecture. Once you do know what the true structure is, then we can use this value that I've mentioned a few times, the RMS deviation, the root mean square deviation. So this gives us a measure of the actual quality of the model. And what it does is to take, in this case, a segment of just 4 atoms, and let's assume that the one in the open circles is the actual structure and the one in the black circles is your model. Now, for each equivalenced position, we calculate a distance. And then the root mean square deviation is exactly what it sounds like. So it is the square root of the mean, which is the sum divided by the number, of the squared deviations. Remember, in a true modelling situation you cannot do this, but once you know what the correct answer is, you can. So summarising some of the information about quality of models and what you expect in terms of root mean square deviations, if the sequence identity is very high, greater than 70%, we expect to have very high quality models, particularly if there are no insertions and deletions. So the root mean square deviation may be around half an angstrom, and that is really equivalent to the accuracy of a crystal structure. If you take 2 different crystal structures of the same protein that have been solved by different people, then typically the RMS deviation may be around that sort of value. Between 55 and 70% sequence identity, we will have high quality models which are likely to have an RMSD below 2 angstroms. And as I mentioned earlier, 2 angstroms is generally the level at which a protein model is likely to be useful. Between 35 and 55%, it's very variable depending on the individual protein. But the RMS deviation is likely to be in the range of 4 to 6 angstroms, and this can be useful for some particular applications, but maybe less so for things like drug design, for example. And below around 35%, remember that was the sort of threshold where we started to get very inaccurate alignments, then we get very poor quality models with RMS deviations greater than 6 angstroms. The main factors then that influence model quality are the sequence identity with the primary parent, in other words, the parent which had the highest sequence identity, the number and size of insertions and deletions, the quality of the alignment, and that of course is hugely influenced by those first 2 factors, and the amount of change that's been necessary to the parent or parents in order to create the model. Every 2 years there's an experiment carried out called CASP, which stands for Critical Assessment of Structure Prediction. Now this is a blind prediction, and what happens is that modelers are given a sequence to model for which the structure has not been solved. Once they've produced their models, then they submit those models to the CASP organisers, and they have an independent evaluation of the results once the structures are available to say how good those models were. Now, just to point out, because this is a mistake that people have made in the past, that CASP is not something that can be used to evaluate your own models. That's the things like Q-mean and analia that I mentioned in the previous slides, or calculation of our RMS deviation once you know what the answer is. CASP is simply an experiment where they use approaches like that in order to evaluate how well people have done. Now, some time ago, I was the evaluator for CASP2. As I said, this runs every 2 years, and CASP14 ran in the summer of 2020. Now, this graph on the right summarizes the overall predictions from CASP2. So along the bottom, we have percentage sequence identity, and on the y-axis, we have the C-alpha RMS deviation. So C-alpha RMS deviation means we're just calculating this on the alpha carbon atoms rather than considering all atoms. Now, you may recall that better than 2 angstroms was something that we're generally looking for, and you can see the 2 angstrom line here. And really you can see then that when you're dropping below about 40% sequence identity, then the majority of the models are far worse than 2 angstroms. Once you're above about 50 to 60%, then the majority of the models tend to be better than 2 angstroms. Now, at 100% sequence identity, I've shown here RMS deviations going up as high as probably about 0.75, 0.8. And of course, at 100%, you'd expect everybody to be perfect. But this reflects the fact that people make mistakes. And this value here of about half an angstrom for 75% sequence identity was what most people got in this experiment. This was an easy protein to model because there was a homologue with very high sequence identity available in the protein databank, and as I recall, there were no insertions and deletions. However, one group missed the fact that that very close homologue was present and chose a homologue instead with a much lower RMS deviation, about 30% as I recall, and achieved an RMS deviation of about 2 angstroms. And in fact, for 30%, 2 angstroms was a pretty good model. Now, I should say that what I have described is really the classical form of comparative modelling. And these days, there are a number of ways that you can approach this problem that don't necessarily follow this classical path. Now, the first 2 steps are always the same: finding parents and performing some sort of sequence alignment. However, there are a number of other approaches that can be taken from that point. For example, using things like restrained molecular dynamics and using artificial intelligence. This is CASP2. CASP14 has just run and the results haven't all been made available yet, but what was clear was that a new method called AlphaFold 2, which was produced by a company called DeepMind, which is a subsidiary of Google, this software is really outstandingly good. Now, there has been stuff in the press and indeed on the radio saying that the protein folding problem is solved. I think that is going a bit too far, because although it's really clearly better on average than all of the other competing methods, it's not completely reliable. So there are structures which should have been quite easy targets to model, where actually AlphaFold 2 did worse than everybody else. When people submit their models to CASP, they have to give some indication of confidence. Now, that's done at a per residue level, but if you simply average all those confidence values, in fact with AlphaFold 2 they were obtaining a pretty good correlation between their confidence and the actual quality of the model. However, in this particular case, while it was the one they were least confident of, it was way off the best fit line correlating the actual performance with the confidence score, and there was really no very obvious reason why this particular model was so bad. Now, AlphaFold 2 makes use of homology where it can, but it's also able to fold up proteins ab initio if it doesn't have a homologue. Now, obviously, it doesn't do as well in those circumstances, but for all these things, it's making use of a type of artificial intelligence known as deep learning. And one of the main things it's doing from that is predicting which residues will contact which. And it's making a particularly good job of that. Now, I'm going to stop the main part of the lecture at that point, and normally I would give you some tips about how to answer an exam question on comparative modelling. But since, as I understand it, you have a capstone assessment this year rather than having an exam, I'm just going to show you one answer, which would be the sort of thing not to write. By looking at the sequence alignment and the secondary and tertiary structure, we can do the 3D model prediction in the software. This was actually an answer that I had to a question asking for an explanation of the classical steps in comparative modelling some years ago. And as you can imagine, this person didn't get very many marks.